Alright, so in this video we're going to start a little bit of a new problem. Shouldn't be anything crazy. Okay, so what we're going to do is we're going to use something's age to predict its height. You know, it could be a person, it could be a dog, whatever. So we're going to start with just 2-year-olds. Alright, so we have a 2-year-old that's 1 tall, and then we have a 2-year-old who's 2 tall. Okay? You know, eventually we'll put some new points out here, but for now let's just leave it at that. And then we're also going to put a W. So this W is a weight value, not weight in like size or like heaviness, weight in terms of like neural net weight or slope. Okay. So what I'm going to do is I'm just going to make a function called W times X. Okay. So whatever this weight is, you know, this is what we're going to use to, you know, this is about what we're looking for. This is sort of our goal, right? We want to find our curve looking about like this, but you know, we have random initializations, so it might look something like, I don't know, who knows, maybe like that. Okay, and let's look at our air surface again. Okay, so how do we make our air surface for this? So we want to figure out, you know, as W changes, what do the errors look like? So as W changes, you know, this line is going to go up or down, and how do these errors change as a function of that? Okay, so how will we do that? We'll say x is now our W, right? So times the, what do we want to do? Times the x value, so that's the x value of a, right? So now this is our function's prediction, and now we want to subtract out the y value of a, so now this is the error, and then we're going to go ahead and square that, okay? So what this tells us is if our weight is 0.5, aka if our slope, this value here, is 0.5, then we're going to get A exactly right. And you might see that already, but if I go ahead and do it, 0.5, boom, it got A exactly right. Because this is the error surface of A. And its minimum, the minimum error happens at 0.5. Okay? So let's go ahead and make our air surface for B as well. Okay, so now I'm going to change these A's to B's. Okay, B. Alright, so now here is our air surface of B, and it's telling us that if our error or our weight is 1, that's going to give us a 0 error on B. And you can probably already tell that's exactly right. So if we make this 1, and that's because, you know, over 2 up 2, the slope is 1. Okay? And then, of course, you're probably already thinking, let's just sum the two up, h of x plus g of x. And this is the sum of our squared errors. Oops. There we go. Okay, so what we can do is let's just find the minimum of that. Let's just do extremum of this curve. Okay, C. C is at 0.75. So if we do 0.75, so I'll just go ahead and type it in here. 0.75, and this is the exact slope that minimizes our squared error, and that's exactly right because it's the middle of these 2 points, right? And so that's and if these 2 points, and we'll talk about this in just a second, so if these 2 points have the same x value, then you want your slopes such that you cross right between them, right? That's going to give you your minimum squared error, okay? And then, you know how last video we talked about, you know, we just clicked and did the extremum and it told us, but in reality, you know, you would use gradient descent or something to get to the bottom of this, to find that argmin, that x value of the min here. When we'll actually talk about optimization methods later, but yeah, so for now we'll just leave that. Okay, so I wanted to show one other thing here. So if you look at these two, you might notice these are the exact same. And that's the same thing that happened in our 1D case, in our one-dimensional case where we were just along this x-axis. And now our parabolas are still the same. And you might wonder, is that expected? And it may or may not be. But I will show you what happens. So let's say we move B to not be at the same x value. All of a sudden, maybe this is a little better example. Yeah, okay. Actually, I want it over here. Yeah, that's a little better. Okay, so now all of a sudden, once I move B, these these parabolas are no longer the same, right? This one's more narrow. And why is that happening? Is it a problem? Why is it happening? Yada yada, right? And the reason it's happening is because since this one is farther out, its x value is farther than a, when we change this slope, right? When we change this thing, since this one is closer, an incremental change in the slope pops it up a little bit, but since this one is farther out, it pops it up way more. So b is more sensitive, right? So a small change in the slope like this pops this one up more. It has more error than this one does, right? So that's just, something to kind of think about. And that's why when they were right here like this, they were the exact same because their x values were the same. But if I move this away, you can see it gets more narrow as I go to the right, less narrow as I go to the left, more narrow as I go to the right, right? So you can kind of just tinker with that. And then, of course, we can still do our summation like that, right? So now it's saying our extremum is at, what is that, 0.83. So now I'll type in 0.83, and you can see that's a pretty good line. In fact, it's the best possible line if you're doing squared errors. So yep, this is kind of sum of squared errors with a problem that has, we have one variable that we're using to predict another one. So thanks.